start. So we had been last talking about rational maps. So it was just a rational map Y is an equivalence class of morphisms from open subsets of X to Y, where two such are equivalent if they coincide on the intersection of these open subsets, or we can also view it as a morphism from a maximal open subset of X to Y, called the domain of phi. And we had defined what the dominant rational map is. That the image of the domain of X is dense in Y. And one can compose dominant rational maps, and one can also pull back rational functions via dominant rational maps. So we have phi of dominant rational maps, and we have the pullback phi star from, if we have phi like this, from ky x, which is just the composition of a rational function, which is the same as a rational map from, say, y to a1 with phi. And we had seen as a last thing that the following are equivalent. No, I forgot to say. So in particular, X and Y are called birational if there is a dominant rational map from X to Y which has an inverse. So rational to Y if there exists phi of X to Y, like this. Rational map has an inverse with inverse rational map. We had seen that the following are equivalent. First, that X is rational to Y. Second, that rational functions on X isomorphic to K of Y as K algebra, and there's an open subset of X and an open subset of Y, non-empty open subsets which are isomorphic. Open subset Y, non-empty, and open with U isomorphic. This is where we ended. I had divided this into two statements, but still. Now, I was just missing a couple of examples. So, just say that a variety X is rational if it is birational to an for some n. rational to define n space. So examples would be, so Pn is rational because it contains An as an open dense subset. Then product of projective spaces is also rational. You know it contains An times Am as an open dense subset. We also, if we take the Caspar-Two cubic, so equal to the 0 set of x to the 3 minus y squared in 2, this is also rational because we had seen that C without the point 0, 0 is isomorphic to A1 without 0. So C without 0 is isomorphic to A1 without 0 by the obvious map. And so they are birational because they have isomorphic open subsets. You can also check as an exercise if we take now a nodal cubic, so a cubic which has a node, for instance, we take C1, which is the 0 set of, say, y squared minus x squared times x minus 1. This is also rational. The real picture will be something like that. So it again has a special point here, which later we'll call a singularity. And this will also be rational. You can try to figure out a map which is defined almost everywhere, which sends this 1. And what is more difficult is, in general, if we have a curve of degree 3, it will not be rational. So one can show, but we can't, yet, that, for instance, if we take C2, set of y squared minus, say, x times x minus 1 times x plus 1, not rational. In fact, most of the time, well, anyway. So, in this case, you, anyway, so this is, but we haven't developed the tools to prove such a thing. I mean, I think it might be possible to make some complicated ad hoc proof, but the way to naturally prove is we don't have. Okay. So for the moment, that's as much as I wanted to say about rational maps, and by rationality, we'll maybe come back to it later. And now I want to start a completely new chapter, which is dimension. So the dimension, obviously, of a variety. So fine study dimension of varieties. And it, if one is over the complex numbers, it should somehow be related to the dimension of complex manifolds. So we would want So the dimension somehow tells us how big the variety is, and somehow, in a suitable sense, in how many directions it kind of reaches. So we would want, in particular, that the dimension of AN should be equal to the dimension of Pn should be equal to n. And maybe we also want that, so how big is, in how many directions it stretches is the same for a variety and an open subset. So if subset X is non-empty and open, want that the dimension of U equal to the dimension of X. And in some sense, whenever if you have a variety and you take a closed subvariety, you really have a condition, so the dimension should go down at least by 1. So if X contained in Y, and X and Y are both varieties, so also both irreducible, then dimension of X should be smaller than the dimension of Y. Okay, now there are several ways how one can define dimension, how one can study it. I will use morphisms to study dimension. So you can imagine if you have a, so study dimension via morphism. So you would expect, if we have the correct definition of dimension, that if, say, X to Y is a surjective morphism, somehow X looks like it's bigger than Y, so we want that the dimension of X is bigger equal to that of Y. And if in addition the fibers of this morphism are all finite, then the dimensions should be the same. We want dimension of X. So now there is a class of morphisms which are both surjective and have finite fibers. So if our expectation here is true, these would be very well suited to compare the dimension of different varieties. And so we will first want to study these morphisms, which are called finite morphisms. So finite morphisms. So I first also say, at the moment it's still the introduction, so I first say what a finite morphism should be. I only define it for affine varieties. So a finite morphism, so say if, well, maybe I can say that. So a finite morphism X to Y will be a morphism of affine varieties is a morphism such that So I can pull back elements in the coordinate ring of y to elements in the coordinate ring of x. So if I take star of, so I have ax, this contains star of ay, subring, because we know that the pullback sends elements in the coordinate ring to elements of the coordinate ring, such that this thing, know this, but this is just a side remark, such that ax is a finite phi star of ay algebra. Now, I haven't told you what that means, so I first have to tell you that. So we start with the algebra. We say I have to define for you what it means for an algebra being finite over another algebra, and then we properly define finite morphisms, and then we use them. Definition. So let A and B be algebras. And I want A to be contained in B. For some elements, B1 to Bn in B, we can look at the A algebra generated by these elements. So denote A 1 to the n. So this is just all polynomials in the Bi with coefficients in A. So this is the set of all G of 1 to n, such that then obviously are elements in B, such that G is a polynomial in variables and coefficients in A. It's a misprint. Okay. So it's clear that this is the smallest ring, or the smallest K algebra, which contains A and these elements B1 to Bn. Because once it contains. Okay. So this is called the A algebra generated by these elements. So now it's this algebra is called finitely generated over A if if I can do it like this with finitely many elements. So B finitely generated over A. I can write it like this. B is equal to A 1 to Bn for finitely many elements B1 to Bn in B. Okay. So this is finitely generated. For instance, if X is a closed subvariety, then if I take the coordinate ring of X, this is the finitely generated K algebra. No, because I can just, in fact, AX written as K, say x1 bar until xn bar, where the xi bar are the classes of the coordinates xi in A of x. Now that follows essentially immediately from the definitions. So this is finitely generated, but we are interested in a much stronger notion, which is finite. So B is finite over R. If there exists, again, finitely many elements, one, two, n in B, such that I can write every element of B as a near combination of these. So such that can be written as B1A plus Bn. Every B in B can be written as B1A1 plus and so on Bn An, where the Ai are elements of A. For instance, a finite K algebra is just a finite dimensional K vector space, which is also an algebra. Much stronger. So is much stronger. Finitely generated. So now this is related to the concept of modules over a ring, which are the analogs of vector spaces over a field. So let me therefore briefly introduce these modules and translate what we have in language. So let me now will define modules and what it means for a module to be finitely generated, which corresponds to this. So definition. So let R be a ring. And for us, a ring always means commutative with 1. In group M with an operation just to note multiplication from R times M to M. So element R in R and an element M in M is sent to Rm. It's called an R module. Well, if it satisfies the same axioms as a vector space over a field. So if I say for all R1, R2, and R and all M, M1, M2 in M, we have that, usual thing, the associativity, the distributivity, and that the one acts as the identity. So first they have R1 times R2 times M. So here I take the multiplication in R, and then the operation is the same as R1 times R2 times M. Then distributive laws. M is in a Boolean group, so we can also add things there. So if I take R times M1 plus M2, R times M1 plus R, M, and also R1 plus R2 times M is equal to R1M plus R2M. Obviously, the ring to addition in the module. And the third one is that the identity in R acts as the identity. So if you think back of your linear algebra course a very long time ago, these are precisely the axioms for a vector space over a field, only that R doesn't have to be a field. So R is a field and R module. Same as a R vector space. Now let's look at some, so now, so an R module is finitely generated if it satisfies the analog of being a finite dimensional vector space. So an R module called finitely generated if there are finitely many elements, say V1 to N in such that, well, the M, it still was called M, such that M can be written as R B1 plus R Bn. Again, every element of M can be written as a linear combination with coefficients in R of these generators. So let's look at some examples of modules so that we see that we have them in our situation. Examples. So first, an ideal ring I in the ring R is an R module. So just we take the multiplication in R as the operation. Property of being an ideal just means that if I multiply any element in I with an element in R, I always end up in I. So this makes it to a module. Then we can also take the quotient by an ideal. So if I in R is an ideal, and A R mod I, then A is an R module. Again, that's clear. We just how do we multiply an element, the class? So if I have an element A in R mod I multiply it by just multiplying the elements and taking the class. So via R times RA is equal to RA. You can easily check that this is well defined and satisfies the axioms. And also, now a bit the other way around than here, if I have a subring of a ring, then the bigger ring is a module over a smaller ring. That's mostly what we're interested in. So if A subset R, so B, subring of a ring, then A module. And this is again via the restriction of the multiplication in B. So these are all quite obvious examples. So in particular, in our situation, if we want to talk about our K algebras, we see the following. So if A is a subring of B and both are K algebras, then B is an A module, and B is a finite A module if it's a finitely generated, so B, which we are also is finite over A, as an A algebra, is a finite A algebra, if and only if B is a finitely generated A module. These are all simple reformulations, but anyway, so far to this. Now I want to start studying this a little bit. We start with a very simple observation that if something is finite over something which is finite over something, then the first one is finite over the last. Then also some slightly more interesting statements. So this is the following proposition. So we take, say, 3K algebra, so let A is subring B, all be K algebras. When I write like this, it means that A is a subalgebra of B and B is a subalgebra of C. Okay, so the first statement is if B finite over A and finite over B, we have somehow some kind of transitivity, then finite over A, we have a partial converse if finite over A, then it is also finite over B. Okay, that's the first statement. And this is quite obvious if you think of it. The last ones are a bit more interesting. So now assume that over A be a finite A algebra. And assume that B is an integral domain. Then every element in B satisfies a monic equation with coefficients in A. So then every x in B satisfies a monic equation over A. So that means we can write x, so x to the n plus sum I equals 0 to n minus 1 x to the I, so ai times x to the I will be equal to 0 for suitable. So we have such a x is the 0 of such a polynomial where the coefficients ai are from A and the leading coefficient is 1. And this also has a partial converse, namely if x satisfies such a monic equation, then the ring that are obtained by adding x to the smaller ring is finite over the smaller ring. So if x in B satisfies monic equation over A, then I take A of B, A of x, finite over A. That statement is actually quite obvious, but anyway, it's useful to know. So the 1 and 3 are quite simple. 2, requires a little bit of linear algebra, but it's somehow make use of the determinant. So first, let's prove it. Yeah. So we assume B is finite over A and C is finite over B. So we have equal to say A1 B1 plus n equal to BC1 M. Well, then, that means every element in B written as such a linear combination, and then every element in C can be written as a linear combination of elements in B with these. So it follows, the statement follows, namely, then as some Bi times Cj. No? So that's yeah. I just put one into the other. And for the other statement is not more difficult. So if finite over A, so then we can write C as A C1 plus n. I and C. Then obviously also equal to BC1 plus, because A is contained in B. If I take a linear combination here with coefficients in A, I can take the same linear combinations here with coefficients in A, but as A is contained in B, it's also one with coefficients in B. So every element in C can be written this way. So second statement is a bit more subtle because, you know, it's a priori not clear where this monic equation should come from. There's no trace of it in the question. No, this is finite over this, and that's it. And so where does the monic equation come from? So we do this, but we use the determinant. That you know from linear algebra. So if R is a ring, and D is some matrix with coefficients in R, a square matrix, n times m matrix with a Dij R, then the determinant is defined by this formula that you know from first knowledge. So the determinant of D, written, for instance, as the sum of all elements in the, right, like this. So we have the sign of the permutation times 1 sigma 1 times one way how one can write the determinant. So all possible ways of combining these. This is an element in R. So what does it have to do? So assume now, so if R is a subring of C, and where C is a ring, and X is an element of C, then I can look at the determinant of X times delta Ij, where this is, you know, this delta Ij is equal to 1 on the diagonal, and everywhere else it is 0, minus Ij. Ij from 1 to n, some matrix x minus d1, x minus d and n, and then otherwise we have here. Okay. So this determinant will be some polynomial. If you work it out, there's precisely one of these summands is this diagonal. So this is the only one which contains n times the factor containing x, or the other ones contain less terms along the diagonals. So it follows from this that I can write this as x to the n plus sum I equals 1 to n minus 1 ai x to the I for sum ai. So this determinant, like this, actually does give me, so this is from 0, it does give me a monic polynomial. So now we have to see what, now we want to somehow find the determinant here. So we want to see that some matrix is something in its kernel, and then we will get this. So let me, where do I have room? far away. So now assume we are in our situation, so we have B the finite A algebra. So assume can be written as A B1 plus A Bn, where the Bi. And we take any element x in B. So then x times Bi obviously is an element in B. And so we can write it as a linear combination of the Bi's. Sum j equals 1 to n Aij. Oh, that's means. And this is where the Aij's are some elements in A. Or I can write this differently, bringing this on the other side. So I have sum j equals 1 to n x Bi minus Aij. So write it better. Yeah, well, I can first write it like this, x Bi minus Aij Bj still equal, is now equal to 0. And I can also write this as sum j equals 1 to n x times delta ij minus Aij, the whole thing times Bj, 0. So we get this, and this is true for all. This is true for all I. So whether okay. So in other words, if I take this matrix here, so this matrix with ij, then the vector b1 to bn lies in the kernel of this matrix. Thus, if I take b1 to bn, this is an element, is a non-zero vector in the kernel of the matrix. I call this matrix M, where M is this matrix. Get here x times delta ij minus aij I, comma j from 1 to n. So this is a kernel with coefficients in R. So this is a matrix with coefficients in R. So we are not so used to work with those, but R is supposed to, so so not R. So the ring was A. This is a this is a matrix with coefficients in B. No? Because X is in B and the Aij are in A, so the whole thing is in B. And B is an integral domain. So we have a matrix with coefficients in an integral domain. We know an integral domain is a subring of a field, so we can view this M as a matrix with coefficients in its fraction field. So viewing M as a matrix, coefficients in the fraction field Q of M, because M is a subring of Q of M. So we know, so if you have a matrix with coefficients in a field, then we know it has elements if it's in its kernel, if it's only if its determinant is 0. So we know that the determinant of M is 0. And this obviously is a monic equation for X. Okay, with coefficients in A. So we see that this, remembering one's linear algebra, helps one out here. And then the last statement was just that if we have an element in the bigger ring which satisfies a monic equation, then if we add it to X, this new ring becomes finite over A. And this is so if we will call this element now B, if B A satisfies monic equation, so n, I just make this noise, b to the n plus sum I equals 0 to n ai e I is equal to 0, then obviously we can bring this to the other side. Then it follows that b to the n is equal to sum I 0 minus sum I equals 0 to n ai b I. So that means every power of b, which is larger or equal to n, can be expressed in terms of the lower powers. And so it follows that that A of b can be written as A plus AB plus and so on plus A b to the n. Every element can be written as a linear combination with coefficients in A of the powers of b until n minus 1. Okay, so far, so much for this finite modules. Now we want to go back to geometry. So I have to define for you what a finite morphism is. I only define it for affine varieties, but more general notion, which is X and Y be affine varieties. Morphism X to Y is called finite if E of X is a finite phi star of A of Y algebra. As I said, we know that the pullback of an element in AY lies in AX, and is compatible with the K algebra structure. So phi star of AY is a sub K algebra of AX, it would make sense for it to be finite. I mean, to ask whether it is finite. I should mention, in general, do not use this for general varieties. So X to Y, morphism of varieties, then phi is called finite. If, hope I get it right, if Y has an open cover by affine varieties, node has such a thing, such that, so which I call maybe VI, if you have an open cover, take a cover of Y by affine open subsets, such that the inverse image fine. Fine. And now I can look at the restriction of the map and phi from phi to the minus 1 of VI to VI. Finite morphism. Fine varieties. So, in some sense, we will only be interested in this. We only need it for affine varieties. The general notion is that you reduce it to that by taking affine covers, but we will not use that. So I first want to translate some part of this position here into statements about fine morphisms. So first I have the remark, if Y in X is a fine space, a closed subvarieties, then the inclusion say I from Y into X is a finite morphism. Because you can easily see that the pullback map via the inclusion is always surjective. So I upper star from AX to AY surjective. So in particular, AX is a finite AY algebra. They're even equal. And I mean, this follows essentially directly from the definition, because AX is kx1 to xn divided by the ideal of X, and this is the same kx1 to xn divided by a bigger ideal, and so this is just the further restriction, and so this is certainly surjective. Now I want to translate some part of the proposition. So let from X to Y, C from Y to Z be morphisms of affine varieties. So if they are both finite, then their composition is. C composed with phi is finite. And this is part of the part 1 of this proposition, namely we have that, what is it? AX is a finite phi star of Y algebra, and AY is a finite phi star, no, let me say it again. Yeah, and AY is a finite phi star of a Z algebra, and so AX is a finite algebra over star phi composed with P star of AZ, because it's precisely this first statement. And the second statement is obviously if I have that under these assumptions, whoever can remember, either the first or the second map also has to be finite. It's very important that one remembers because only one of them is right. So the statement is if psi composed with phi is finite, then phi is finite. This is the translation. If C is finite over A, then C is finite over B. Because here we have that AX is a finite C composed with phi star of AZ algebra, then it is also a finite algebra over phi star of AY, because this one was finite. Okay. So these two are just a translation of the previous proposition. Part 1. Just as an example, because we use that often, in particular, if x to y is a finite morphism, and we take a closed subset in the image, there is a closed subvariety, then phi as a map viewed to W is also finite. Because this phi here is the composition of this one with the inclusion of W in Y, and we apply this statement here. Okay. So now we want to find out some nice geometric properties of finite morphisms. And so our first goal is to show that finite morphisms are closed. We had seen that, morphisms from projective varieties are closed, but this was a very special property for projective varieties. If you have morphisms from affine varieties, they have a strong tendency never to be closed, but or often not to be closed. But finite morphisms are closed. So the image of any closed subset is closed. So we want to see that. So finite morphisms are closed. Our next aim. So we have the following remark, which is just a simple reformulation of what we know from the Nullstellensatz. So if X in AN is a fine variety, I, in the coordinate of ring, is an ideal, which is not the whole of AX, then zero set of this ideal, by which I mean the set, I mean the usual thing, this is the set of all p in X, such that f of p equal to 0 for all f in I. This thing is not empty. Okay? And this is basically just the usual Nullstellensatz, except that for the Nullstellensatz we said it for kx1 to xn. We didn't talk about coordinate ring, but we just image in kx1 to xn. So let me say this. So proof so take the canonical projection pi from kx1 to xn to ax. Then p to the minus 1 I is a proper ideal in kx1 to xn containing the ideal of x. I, for security, will assume that x is not empty. So then we know by the Nullstellensatz so zero set of p to the minus 1 of I is not empty. Obviously, this is the same as the zero set of I. So a priori, because I mean, from the definition it follows that this is the same zero set. So so now I want to show that finite morphisms are closed. Not but it's not too difficult. First, we simplify our situation a little bit. So let say f from x to y be a finite morphism. And it's always understood that this means of affine varieties. So we are supposed to take a closed subset, and we can assume, if we show this, then the image should be closed. If we show this for a closed irreducible subset, that's enough. So we have to show that f of w is closed in y. So let z y be the closure of f of w y. So as we are supposed to show that w is that f of z that f of w is closed in y, we therefore have to show that Z, that f of w is equal to z, to z. So to show f of w is equal to z. So we can therefore replace x by w and z and y by z. Then we have to show that the map is surjective. So replace x by w, y by z. So we can assume thus that f of x ends in y, and we have to show that f is surjective. So by the things I said here before in this remark, it follows that if f from x to y is a finite morphism, that also f restricted to z from w to z is a finite morphism. So now we have to show this map is surjective. And so to show that something is surjective, we take a point in. So first, we use the homework that you had, namely as f of x is dense y, we get that f star, pull back by f from ay to ax, surjective. So for simplicity of notation, I would just identify ay with the corresponding image in ax. So just for notation. Okay. So we can assume that y, x and y are affines. We can assume that y lies in some an. So let y subset an subvariety. So we have the coordinates. So, and we take a point, a1 to an, y. We have to show this point lies in the image of the map. So let's look at the ideal of functions which vanish there. So for instance, we put m equal to the ideal generated by, actually somehow the x1 minus a1 until xn minus an. So here I really mean I take the class in a y of this, which I look at this ideal, which is an ideal in a y. It's clear that the zero set of this ideal is just the point P. No? So now we want to see what is the inverse image. How can I describe the inverse image under F of this set? We want to show that the inverse image is non-empty. So we denote by ax times m. So m is this ideal. Now we take I take the ideal generated by M in this bigger ring. No, we know that AY is contained in AX, so I can look at the ideal generated by M in this bigger ring. So this is just set of all AM with A in AX and M in M. And notice this can also be, so this is the, as I said, the idea generated by M. And notice that this is the same as the ideal generated by these generators. So this is just the ideal, like this, generated by the corresponding classes in AX of x1 minus a1 to xn minus an, but now as an ideal in AX. So we look at this ideal, so the ideal generated by the same elements in this bigger ring AX. AY is contained in AX. And now, so what does it mean to lie in this ideal? It means that, so now I have to, actually, I don't like this so much, this rotation. I want to see whether not sure I like this identification. Maybe I yeah. So well, okay, maybe I can stick to it. So we have this. Now we have to remember that we made this identification. We identify any element in AY with its corresponding pullback here. So that means that what is really written here is, so if we take the zero set of this thing, if we take f to the minus 1 of e, what is this? This is the set of all q in X such that f of q is the same as the set of all q in X such that, it means that the ith coordinate of f so that means if I take xi minus ai composed with f 0 for I equal from 1 to n. Now our identification was that I just identify xi minus ai composed with f. So this is just the zero set of this thing. Composed with f, but this I had identified away. But now the zero set is in X. And so that means we have to take, so the ideal is now generate, so we take the zero set of these elements, which is the same as the zero set of the ideal generated by it in AX. And so this is Z. of AXM. So you that, so then we have here, we have found that the fiber is the zero set of this ideal generated by the same M, or strictly speaking, by AX F star M. Yeah. So therefore, it's enough to show. So we want to show that this is. We have to show that this is non-empty. So we have to show. And so we are therefore reduced to the following lemma. Which is the following. Maybe I write it, we have a bit more room. So lemma, take that A algebra, your finite A algebra, in our case B is AX, A is AY, or strictly speaking F star AY. Main. Fine in our case because B is AX and AX is a variety, and so the coordinate ring is an integral domain. And take a proper ideal in I. Proper ideal. As we are given here, this is this M. Then PI, proper ideal. Okay. So we want to show that. And so then, if it's a proper ideal, then again, the Nullstellensatz tells us that so here we wanted to show that this is not empty, which is equivalent, so that AXM is not equal to AX. No, because we had just this version of the Nullstellensatz, which tells us that then the zero set is empty, is non-empty. So now here we have again the story with the integral domain. This is maybe a hint that we again use the determinant in a very similar way to how we used it before. So proof. So first we write down very similar things to before. So we assume by contraposition or by contradiction that it's not true, so that, or yeah, by contraposition, we assume that BI is indeed equal to B, which okay, then we have to show that I is equal to A. So so B is finite over A, so we can write B equal to AB1 plus ABN for some elements BI in B. And so therefore, B is equal to BI. So we okay. So BI is obviously, this is commutative, no, is equal to IB. And so we can multiply every element in B with an element in I, and so the element in A becomes an element in I in each of these cases. So this I can write as I B1 plus I Bn. Okay, so every element in B can be written as a linear combination of these i's with coefficient in the ideal I. So, and now we write this out again for our BI's themselves, and we will get again a matrix. So we get I can be written as sum j equals 1 to n aij, where now the aij are actually elements in I. And now we write again this matrix M. Now we don't need an extra x, we just write M to be matrix delta ij. So 1 on the diagonal, 0 outside, minus aij. I j goes from 1 to n. So we have this matrix, and then we see again, if I take the vector b1 to bn, it lies in the kernel of this matrix. If we do this, if we write b1 to bn to this, we get precisely this thing that we get bi. So in the ith formula, we get bi minus sum j equals 1 to n aij bj. And this is supposed to be 0 for all I. And so this is precisely the statement that b1 to bn lies in the kernel of M. So again, we can view this as a matrix with coefficients in the fraction field of B. So therefore, now I also called that thing M. Obviously, this has nothing to do with each other. So M coefficients in Q. And so it has something, a non-zero element in the kernel, so the determinant is 0. So then the determinant of M is equal to 0. Now we have to see what that means. So what is the determinant of M? So I claim, if I look at this, so how does it look? We have here 1, 1 minus a 1, 1. And here we have j's, a and n. We have this. So we have this one term where we could take the diagonal, so we get a 1, and then we get some combination of these aij's, and all other terms are divisible by aij. So we get that this thing is of the form 1 plus sum L, where BL is an element I, because every other term contains at least one factor aij, and the aij's lie in I. So 0 is equal to 1 plus some combination of elements in I. So that means we bring this to the other side, thus it follows that 1 is an element in I. Thus I is equal to A. We have seen that if BI is not a proper ideal, if BI is equal to B, then I is equal to A. And this then concludes that finite morphisms are closed. Okay, so maybe it's a good moment to stop. Next, I will make some applications of this. So, okay, so are there any questions? Otherwise, I wish you a good weekend, also success for the differential geometry exam, if you, for those who do it. And it might be that next week we actually will be able to see each other in the here in the room. I mean, at least I heard something that maybe next week we will have in-person lectures. So maybe that will be nice. Okay, so have a nice weekend.
Thank you.
Thank you.